This picture is a picture of a graph. This is the sea of nodes representation. So it goes from the start to the end. Control flow flows from the start to the end, and data flows from here, right? So you probably can't see a single thing. There, yeah, you can see everything now. Okay, this is a function that takes in an extern pointer. So this extern pointer is C semantics or something. Anyway, data flows. This control flow flows here. And since control flow is not diverging anywhere, you can expect all these things with dependencies to execute basically atomically. That's a really nice property of sea of nodes, is that you can set up these dependencies. These dependencies will depend on each other, but if control flow doesn't diverge or go anywhere else, they all execute at the same time. And when I say at the same time, I don't mean literally at the same time. It's just a mental model. It's just a mental model, really. This is flow of information, not flow of control. Flow of control goes from start to end. This is flow of information. So yeah, you're selecting one, and you got these two arrays. You index, and you go to a subregion. That's another subregion. You store to a const. You union to get another subregion. You store into that again, and then you store into this again. It's a nice representation. Uh, but that didn't end up working out for me. This umbrella project. Okay, take a look at this canvas. This is sea of nodes. So I'm currently just formulating. I'm going from left to right, left to right, left to right, left to right. Wow, it's just laggy, so laggy, until I get to something like this, right? F takes in a pointer to an i32 immutable one and returns an i32. And this is a global variable. This pointer to an i32 has no region, has no specific region marker, which means this cannot alias with this. You cannot pass a pointer of this into this while still mutating it here. Alright, so you can see F binds to EX, which equals a do block, global equals 30, EX equals 20, return global. Now let me move this in here because my camera is probably blocking it. Yeah, return global, and then main just calls it. Anyway, so it goes to the start. You have a pointer to a global and a pointer to an EX. The pointer to a global is a hidden parameter to the function because you're affecting it in its global state. Anyway, it goes start pointer EX. You're storing a const of 20. Global goes from you're storing a value of 30 into a store. This is an effect that has to be propagated to the return, but this mutated region you're passing into a load, and that load loads a value and you're returning it. Now you can easily tell that there is no control flow here, and these two loads happen simultaneously of each other. There is no dependencies at all. So if I go to the scroll up version, this is the optimized version. What you can do now is remove the load. So if you look at the bottom, this start goes to the end, pointer goes here, you're storing a load, you're storing a value, and that propagates into the load, right? Because the load depends on the store, and then you're just returning it. But what you can do is the load isn't clubbered at all. So what you can do is you can constant propagate all the way up here and just remove the load and replace that with a 30. And you wouldn't be able to do this if you didn't know that these like alias at all. So you can see the pointer right to the EX and the pointer right to the global, they happen simultaneously of each other. That is regions. This is a really nice way to explain regions in my programming language. Regions, you know for a fact that they are not going to alias. That means they can happen independently of each other with no dependencies. So you can see, I mean, it makes sense, right? There's no need to reload the global because it's not going to be overwritten by this pointer access. So you can just do return 30. This is essentially the transformation that it's doing, return 30, and you're still writing to the global anyway. All right. This graph format is really nice for representing data flow, right? The flow of data goes from the start to the end. That's control flow. But with pointers. With pointers goes to the storing and loading, and these things happen independently of each other because they're in different regions. This is a nice way to represent storing and loading and all these things like that. And this is called a sea of nodes approach. It's a whole bunch of nodes, and they're all they all depend on each other, and that's how you represent these data flow. And then things like where is this? Things like an if statement. Yeah, things like an if statement. Control gets passed here, and the parameter C if has two branches, true and false, branches to a region. And this region is connected to a PHI node, true or false, and then control gets propagated to the return. Seems very intuitive because, yes, it is quite unintuitive to a normal compiler developer, right, who doesn't really work with graphs like this. They work in a statement-based, structured, static form. This is really hard for me to understand. I'm gonna say it short. I mean, I've done all these graphs, right? I've did my research, and it's really fucking hard for me to understand um these these transformations and optimizations just from looking at it. That's actually quite easy, right? This is just another way to represent static single assignment form. uh all SSA and sea of nodes and all of these things, they represent the flow of data with respect to control flow. Same thing. This is the same thing. You still got the PHI nodes and everything. Uh, but it's just it's not a malleable thing to work with and understand, right? Right. I got a statement. I can't, in my brain, I just can't really think of all of these webs of nodes and all this interconnected thing is. I like to think of a top to bottom. Right? I like to think top to bottom with my intermediate representations. But this is a nice introduction to Sea of Nodes. The reason why I was telling you this is, for one, I spent a lot of time on it, so I got to tell you. But the reason why I'm telling you this is because it's a nice way to represent the flow of data, and the flow of data when they can happen simultaneously, mutually exclusive of each other. That's regions, right? I hope you understand how, if I have two parameters and they're in a different region, you can write to this one, and you can reorder them. They don't depend on each other. That is the one of the best things about regions, and I think I explained it well, because you can see these two diverging paths. Okay, best way to explain it is for me to cook up an example. Block parameters. All right, so you have a function f, takes in a bool, returns an I32. F c equals if c 30 else 20. Pretty simple. All right, and inside this is an SSA form. I'm gonna do it in a static single assignment form with like PHI nodes that you're used to seeing, specifically in LLVM and things like that. All right, so you have an entry block. So like function f main.f, and it has a, what's it called, c, which is a bool. Okay. On entry, you're gonna do if c go to, and then what's it called, block. Yeah, so the control flow will split off. So block truth and block false. So true and false go to block T, else block F. Okay, and then you do is exit. So in block T, you're gonna go to exit. In block F, you're gonna go to exit. And then inside here, we do like, this is just the v0 is just the normal thing, and then we do phi block T. So if it goes to block T, it's 30. If it goes to block F, it's 20. And then we just do a return v0. Make sense? I think this makes sense. So F is a bool, returns an I32. F binds on C. If C 30, else 20. And then in the function, it goes into an entry block. So this is the terminator, like the br if, branch if. If C, then go to block T, else block F. Then inside you just go to exit. And when you reach exit, you come with a PHI node. So this is where these control flows they diverge, and you can This is data flow with respect to control flow. So, so like if you came in from block T, you get the value 30. If you came in from block F, you get the value 20. It's a very simple explanation of phi nodes. And what you could do instead is you can use block parameters. This is something not new. The Swift language uses it, and MLIR uses it. MLIR is the successor to LLVM, which means they know what they do. They know what they're doing. They know what they're doing. And when they know, yeah, which means block parameters has a certain amount of weight to it. If LLVM out of all things are moving away from SSA and PHIs and into block parameters, you know they they really mean it. Okay. Okay, and then there it is. Exit takes in a v0, which is my v2. All right, these two are equivalent. They may not look equivalent, but they're essentially equivalent. So if C, then go to exit 30 with a block parameter of with a block parameter. Go to exit with a block parameter of 30. Else, go to exit with a block parameter of 20. When you get to exit, v0 will be I32. Return I32. These, believe it or not, these things are equivalent. They are completely equivalent. They represent the exact same thing, except a block parameter form is just nicer to work with. They represent the same control flow, the same data flow, the same static single assignment, everything. And when I saw block parameter, I was like, oh, I didn't really think too much about it. But when I really thought, what really turned me off from using this representation with explicit PHIs in my compiler is because PHIs are really fucking annoying. They are so annoying to work with, because even the LLVM and MLIR developers, I mean, they talk about how they have to write specific things to skip over PHI instructions. You need to make sure PHI instructions stay at the top and all these things. If Chris Latner, the guy behind Mojo Swift LLVM, is saying use block expressions, use block parameters, use block parameters. I think they're a lot nicer. Oh yeah. So what you can do with a block IR is I think you do like go to. You can have like syntax sugar that you expand. It's like instead of this well, okay, the first problem. How do you represent pattern matching in a statement by statement control flow IO? How do you represent pattern matching? Because you don't want to unwrap the pattern matching, because you need to check, is this pattern matching right according to the type? Are these I32s, right? You're gonna lose information if you unwrap it to like switch statements or too quickly. So when you get to here, what will generate in the parser is function add, takes an I32, returns takes an I32 and I32 returns an I32. The entry block has the parameters P0 and P1. And what you can do is you can use this kind of like this abstraction, this go-to pattern abstraction that will later on, after the type check, can be expanded. So go-to pattern P0, P1 to labels add 0 and add 1. And I mean, it like isn't this really intuitive? So add is a 0 0. It takes nothing. It just go to with ret 0, and then add the add branch, add the 1th index branch takes in an A and a B, and then v0 A plus B go to ret. This is a really nice way to do abstractions, because currently I'm not unwrapping the pattern. Later on, after in type checking, I'm going to unwrap this go-to pattern into if statements, switch cases, and all these things. But you can retain this abstract information from the parser. You can retain it and then unwrap it later on.